Did you know that the faster you move, the heavier you get? This is actually explained in Einstein's theory of relativity. Marhaba! This is Mr. Jesse and welcome to another episode of Physics is Easy with Mr. Jesse. This lesson is on Chapter 28, Section 3, the Bohr Model. For this lesson, we will cover the following objectives. First, state the basic assumptions of Bohr's model of hydrogen and derive the energy levels from them. Second, define ground state and ionization energy. We will also relate the energy levels obtained from Bohr's model to the Rydberg equation, state Bohr's correspondence principle, and lastly, to apply Bohr's model to hydrogen and hydrogen-like atoms. At the beginning of the 20th century, it wasn't understood why atoms of a given element emitted and absorbed only certain wavelengths. In 1913, Bohr provided an explanation of the spectra of hydrogen that includes some features of the currently accepted theory. His model of the hydrogen atom included the following basic assumptions that are being discussed on the next slide.
Hello everyone. Today we'll be looking at a little more detail at Bohr's atomic model, which he used to describe the structure of the hydrogen atom. Unfortunately, he couldn't really extend it to bigger atoms, but it was still pretty good. It was the first model to ever use quantum physics. So, without further ado, let's get started. So Bohr's 1912 model used a radical new quantum physics, which was still pretty controversial at the time, to explain spectral lines. So it was the first time quantum physics was ever used with a sort of actual real application other than explaining blackbody radiation. And in fact, the first time it was used to describe particles like electrons instead of just packets of energy. The model consisted of three main postulates, all of which were pretty crazy at the time, but all worked really well together to explain the spectrum of hydrogen. So the first and biggest postulate is that electrons can only occupy certain energy states. They're not just orbiting around a nucleus, but they have to be at certain energies around the nucleus. They can't be anywhere in between. And that's sort of the main quantum physicsy bit. So the electrons around the nucleus do not radiate energy, as classical physics would have them do, but instead they're sort of stuck at each state. They can't move in between. So electrons in different orbits have different energies. So the lowest orbit will have the lowest energy, and it won't be able to spiral inwards, and it won't be able to spiral outwards. It can only jump. So Bohr's second postulate defines what these allowed energy states were. So we have energy level 1, 2, 3, 4, and so on. So the equation he came up with was this one here. mvr, which is the angular momentum of the electron, equals nh over 2 pi. So mvr is the electron's angular momentum. Fairly important. This is sometimes known as the rule of quantized angular momentum. And the integer n on the right side of the equation is called the electron's principal quantum number. It corresponds to the energy level of that electron. We can see that there are a few other letters in here, so I'll just quickly go through them. H is Planck's constant, which you should be familiar with by now. Pi is the circle number, 3.14-ish. And so this means that the energy level, the quantum number of the bottom energy level is 1. And so the angular momentum here will be given by this expression. So this will be h over 2 pi. This will be 2h over 2 pi, and so on and so forth. Now at first the units might look a little odd here, because you think, hang on, integers and constants like pi don't have units, but Planck's constant is in joule seconds. How does that work when angular momentum is given by this equation, which is kilograms meters per second times meters. Well, it turns out that 1 joule is the same as 1 kilogram meter squared per second squared. And so if we multiply this by another second, then it'll match up exactly with this expression here. So that means that although they at first look different, the units on both sides are equivalent, which is pretty important when we are making a new physical law. So Bohr's third postulate, we're still on the postulates, explains the spectral lines of atoms. And this is what allows electrons to jump between energy levels. The postulate says that when electrons change their energy level, they absorb or emit a photon. If they go from a high energy level to a low energy level, they emit a photon of energy. If they go from a low energy level to a high energy level, they can only do it if they first absorb a photon of energy. They sort of make this jump, as you can see. So the energy change is equal to the energy of the photon. It makes sense, right? But you need to write these things down if you're making a whole new theory. So we can see that the change in energy, which is the final energy state minus the initial energy state, will be equal to the energy of the photon, hf. So this was the first model that could successfully describe the spectral lines of hydrogen, which is pretty good because up until that point they were a little bit of a mystery. It was also the first model that used quantum physics to describe some aspects of the atom. Everything before that had been using classical physics. The model still had a number of flaws and problems. It was a big step forward, especially for using quantum physics to model the real world, but it was far from perfect.
Now let's talk about the relevant equations of Bohr's atomic model. The first equation is the radius of the atom, or the radius of the electron's orbit. Now this equation is based on the assumption that the electron can only exist in certain allowed orbits. So he was able to come up with a mathematical formula, and it is this formula over here, where r sub n is the allowable radius, and n is an integer, 1, 2, 3. H bar is just equal to the Planck's constant divided by 2 pi. Ke is the Coulomb's constant, and that is 9 times 10 to the power of 9 Newton meter square per Coulomb square. E is the magnitude of the charge of electron, 1.6 times 10 to the power of negative 19 Coulomb. And Me is the mass of the electron, that is 9.11 times 10 to the power of negative 31 kilograms. Also, I would like to point out that the N here is actually the energy level. So for example, Rn simply corresponds to the radius of each energy level. So for Rn is equal to 1, or when n is equal to 1, the radius, or the orbit has the smallest radius, and this is called the Bohr's radius, or a sub o, and it has a certain value. So if we are going to substitute n here with 1, and then this quantity here is actually a constant, so therefore r sub 1 is equal to the Bohr's radius, and it has this value. Then this tells us that we could express this formula, this general formula, in terms of Rn would be equal to n squared, or the energy level, multiplied by the Bohr's radius, or we could say Rn is equal to n squared multiplied by 0.0529 nanometers. So here is a representation of the radius for each orbit, and it follows the general expression r sub n is equal to n squared multiplied by the Bohr's radius, where n is the energy level. That's the energy level. So if we have here the proton, this is a proton, and we have here the electron, the radius of the first energy level is just equal to the Bohr's radius. Now the radius of the second energy level would be equal to 4 multiplied by the Bohr's radius, and also for the radius of the third energy level, it's going to be equal to 9a sub 0, or 9 multiplied by the Bohr's radius. At this point, kindly go to WebAssign and work on the task entitled the Bohr's model part 1. So for this task, I need you to take note of the relevant equations included in the tutorial exercise. These equations would allow you to solve for the linear momentum of the electron, the angular momentum of the electron, the kinetic energy, the potential energy, and the total energy of the atom.